Do I have any questions on assignment number 6 out of the book there?
Can you work out number 33?
Yep. All right, so 33 says the integral from -1 to 1 on 1 minus the absolute value of x dx. Okay, so at this point, we only know how to solve these by graphing. Okay, so I'm going to plug -1 in. Okay, so when I plug an x value of -1 in, I'm going to get the absolute value of -1 is 1, and 1 minus 1 is 0. So at -1, I'm at 0. Okay, I'm going to plug 1 in. Okay, and I'm going to get the same thing, 0. Okay, I got to find that vertex point because obviously there's another point somewhere in between. So if I plug 0 in, I'm going to get 1. Okay, and that's that vertex point where we turn right there. So it's just that triangle, base from -1 to 1 and a height of 1. Okay, so it's 1/2. The base is 2 units long and the height is 1. And that gives us 1. All right, anything? Go ahead.
On like 46 and like 49.
Okay.
Can you just explain what you're supposed to do since there's like A, B's, and C's?
Yeah, they're just different questions. Okay, so like 46 is giving you this information up here, the integral from 2 to 6 on f of x dx is 10, and the integral 2 to 6 on g of x dx is -2. So on this one, you're adding those two answers, 10 plus -2.
Okay, I got
And then
it.
so on. And then 49, you're just using that same picture that I actually did in the notes, and you're doing the same thing. You're just answering questions about this.
All right, got it.
Sometimes it gets confusing and it looks like it might be a multiple choice question, but when it's not, it's really just 4 separate questions. All right, anything else? Okay, all right, so today our new notes are going to be on what is called the fundamental theorem of calculus. If you have your foldable handy, which I hope you do, because you should have that handy all the time, but we are going to put something in there at some point today. Okay, so we are starting this thing called the fundamental theorem of calculus. Obviously, it's important, right? Okay, it's the fundamental theorem of calculus. Okay, and we're going to make some connections. We're not going to get through this whole packet again today. Okay, it's going to be a 2-day process. There's like 8 pages in this section. Okay. All right, so first of all, we have the velocity of a car is modeled by the function v of t equals -30t plus 90, where t is the number of hours since the trip began, and v of t is the velocity in miles per hour. Okay. Question 1 says, graph this function in the domain 0 to 5. Okay, so if I plug 0 in, I'm going to get 90. We'll plot that point. All right, next one, we're going to plug 1 in and get 60. I know the graph is hard to see. It didn't print out well for me either, but we'll do our best. All right, when we plug 2 in, that gives us 30. When we plug 3 in, we get 0. When we plug 4 in, we get -30. And when we plug 5 in, we get -60. Okay, it doesn't matter if it's that straight. I'm just going to do it so it looks nice. But there's our velocity graph. Okay, and remember we talked about yesterday when we integrate velocity, or when we integrate speed, we're going to get total distance traveled. When we integrate velocity, we're going to get displacement if any part of that velocity graph is negative. Okay. All right. Using correct units, explain, or no, first, I'm sorry, number 2. find the integral from 0 to 3. So we're just finding the area of this positive stuff right in here. Okay. So as of right now, we only know how to do it with geometric formulas. So it's a base of 1/2, or excuse me, it's 1/2 times a base of 3 times a height of 90. And what 90 times 3 is 270. Half of 270 is 135. All right, so that's so far we've done that. Okay, number 3 is asking us, using the correct units, explain what that means in the context of this problem. Okay, can anybody help us out on that? What does the integral 0 to 3 v of t dt mean?
That's the base.
Okay, but in the context of this problem, okay, what is getting 135 mean, which is the area of this triangle? When we integrate velocity, what are we getting?
Miles an hour.
Not miles per hour. Good guess. Miles per hour would be just velocity, right? But when we integrate velocity, we're really finding so integration means antiderivative, right? Okay. What is the antiderivative of velocity?
Position.
Position. Okay. But when we add up all the positions, right? Because what this is a sum, right? When we add up all the positions, what do we get?
Displacement.
Okay. Displacement is not incorrect. Okay. It's going to be total distance traveled because this is all positive. Okay. Displacement would be if we ended up having negative area, right? So if velocity is always positive, then we're just continuously moving to the right and we're moving away from where we started. As soon as velocity becomes negative, like it did right here, okay, then we're going to start moving back towards our original starting spot. Okay. For example, okay, you come to school, let's say you come to school every day, right? Okay. Your total distance traveled is actually probably 0 if you took the exact same route, right? You drove to school, you stayed here for a while, and then you drove back home. Well, if you took that exact same route, your displacement is 0, okay? How far you are from where you started. But your total distance travel will be how far it took to come here and how far to go back home, okay? So when everything is positive, then we're going to just be total distance traveled. So to write this, we're going to say the car traveled 135 miles during the time t equals 0 to t equals 3. And then we'll say hours since they told us and they asked us to use correct units. Okay, so it's the total distance traveled in those very specific 3 hours from time t equals 0 to time t equals 3. All right, next we're going to find the integral 3 to 5 v of t dt, which is, we got to know this is negative, right? Okay, when we're below the x-axis, this is negative. We're still making a triangle here, okay? Just pretend we have that right there. Excuse me. Okay, so this is going to be negative 1/2. My base is 2, and my height is 60. Okay, 2 times 60 is 120. Half of 120 is 60, so negative 60. All right, remember, when velocity is positive, we're moving to the right or moving up. When velocity is negative, we're moving to the left or moving down, okay? Cars don't go up and down, right? They only go left and right, okay? So What does this negative 60 mean in the context of this entire problem? So from time 3 to 5 hours, what did the car do in from 3 hours to 5 hours?
Traveled 60 units
Okay, and
in the
which
opposite
direction?
direction.
Okay, so not okay, the opposite direction of what it traveled from 0 to 3, right?
Yes,
Bas-
sir.
Basically meaning we're just going back towards where we came from, most likely, right? Because we're going back to the left. So if you just picture we're going right and left the whole time, we're going back left. Okay, so the car traveled 60 miles back towards where it came from or where it started. During the time t equals 3 to t equals 5 hours. Okay, so if we're thinking about this problem, we drove 135 miles away from wherever we started. So at time 0, we were at 90. We drove 135 miles. Okay. And then we drove back 60 miles. Okay. The next question is find the integral 0 to 5 v of t dt. Well, from 0 to 3, we got 135. And from 3 to 5, we got negative 60. We add that up and we get 75. Okay, so 75 miles is our displacement. Okay, and that's really question number 7 here. Displacement is defined as the distance an object is from where it started. From wherever we started, we went 135 miles to the right, and then we went back 60 miles to the left. Okay, so our displacement is 75 miles. We are 75 miles away from where we started. And that is the same thing as this integral right here. By the way, what we're getting at today with the fundamental theorem of calculus is going to be that we are now going to be able to get exact values on these integrals. Okay, so when we just to recap, we started with curves, and we had LRAM, RRAM, MRAM, and trapezoid method. Okay, those are all called Riemann sums, different methods of them. And all they did was estimate. Some of them overestimated, some of them underestimated. Okay, and each method that we did, starting with LRAM/RRAM up to the trapezoid method, we kept getting closer and closer to an exact answer because we started minimizing that over or under amount of area that we were counting when we found our area. Okay. Then we learned starting on Monday, we just did geometric formulas. We would just actually sketch a graph. Okay. And then those graphs that I gave you over the last 2 days, Monday and Tuesday, and then in the homework, you were getting geometric formulas that you knew the formula for to find the area. Okay. So now we're going to be getting to, although we're still doing like triangles right now up in here, we're going to be getting to actual curves where we can't just find with geometric formulas. And we're going to use what's called the fundamental theorem of calculus. All right. So now that whole thing right here was all about velocity. Okay. The next thing we're going to do is we're going to talk about position. Okay. So right up here at the top, it says the position of the car described in questions 1 through 7 is modeled by this. Okay. And we can verify that. Okay. What is the derivative of this function? So we're going back right to last semester. The derivative is take this exponent, multiply it by your coefficient. So 2 times negative 15 is negative 30. Subtract 1 from your exponent. And the next one is 1 times 90 is 90. Subtract 1 from your exponent. And then the derivative of 8 is 0. And you can go back and look. The velocity function was negative 30t plus 90. Okay. So here's our position function, negative 15 squared plus 90t plus 8. Okay, we're going to need a calculator to get some of these values. So we're going to graph it, okay? When we plug 0 into this, okay, we plug 0 in, we're going to get 8. Okay, so 0, 8 is right there. Okay, can anybody tell me? Oh, well, we're actually going to do that in question 9, so I'm not going to ask you yet, but start thinking about what that means. All right, the next point, I'm going to actually just graph this real quick in my calculator so I can pull out the points quicker. Negative 15x squared plus 90x plus 8. All right, so at 1, we're at 83. It's kind of rough estimate on where it's at. At 2, we're at 128, just under 130. At 3, we're at 143. At 4, we're back down to 128. At 5, we're at 83. Okay, and being that these are the same distance apart and they're at the same y value, that is going to tell us that that's our vertex, okay? So we're going to look like this. We're not 100% sure if that's our vertex, but remember the axis of symmetry goes through your vertex, and so these points should be equidistant and at the same y value, and they have the same y values, so that is our vertex. All right, so this question number 9 is asking, what does S of 0 mean? Okay, remember, this is the position function. Okay, who can tell me what that means?
Position at 0.
Okay, yeah, that's your position at 0. Okay, so at time 0, we haven't moved yet. The car hasn't moved. We're 8 miles. Okay, and that's going to answer this number 10 here. Okay, we're 8 miles away from the starting position. So let's just say we're 8 miles away from our house. Okay, and then we're going to start going somewhere. All right, so this is equal to 8, and this means the car started 8 miles from the starting position. Okay, we found S of 5 to be 83. Okay, so this one is 83. So using correct units, the context of that is the car is 83 miles from the starting position at time t equals 5. Okay, so don't confuse total distance traveled or distance traveled with this one, okay? When we're doing position, that's a very specific spot we're at, okay? That's not adding up, okay? When we're integrating, we're adding up all those positions, and when you add up all your positions over time, okay, you're going to get the total distance you are away. All right, so here's where you need to start making these connections to what's going on between the two functions, velocity and position, and what we're doing when we're integrating, okay? So S of 5, we found to be 83. S of 0, we found to be 8. And 83 minus 8 is 75. Have you guys seen the number 75 today?
Yes.
And what was that 75?
The displacement.
That was the displacement, okay? So displacement is defined as the distance an object is from the starting point. We've already talked about that. Displacement from time 0 to 5 is 75 miles, okay? But the key here is this thing right here, okay? All right, so what is the relationship between S of t and V of t? Okay, there's two different relationships, right? S of t is the what of V of t?
Derivative.
No, not the
Oh.
derivative, the
Anti.
Antiderivative.
antiderivative, right? Position is the antiderivative of V of t. And going the other way, V of t is the derivative of S of t, okay? All right, so if, as you're finished writing that up, if you go back to the other side and you look at question number 6, we found the integral 0 to 5 v of dt. What did we get for that?
75.
75, okay? In question number 13, we found S of 5 minus S of 0, the position at time 5 minus the position at time 0. And what did we get?
75.
Correct. Okay. So what you have just figured out is this right here is the fundamental theorem of calculus. So if you have your foldables available, okay, we're in this section called integrals application. However you guys printed it, it doesn't really matter how you folded it, okay? But in there somewhere is the fundamental theorem of calculus. And we're going to go ahead and place that in here now. And the fundamental theorem of calculus part 1, because there is a part 2, is the integral from a to b on f of x dx is equal to f of b minus f of a. Okay. I'm sorry, this should be f prime, not f prime. Okay. Because that's going to be like our velocity. So the antiderivative of velocity is going to be the position function. Okay. And that's just one application to this whole thing. Okay. It's the one that we use a lot though. All right, so it's written down here again on the next page. Does anybody need that foldable anymore? All right, so we've been introduced, okay, so we're going all the way back into August now, okay? We've been introduced to the two branches of calculus now, okay? There are two types or two sides to calculus. There's differential calculus. We did that all first semester, derivatives, okay? And then starting right at the end of in the beginning of January, we started working on integration, okay? And more recently, we've been doing definite integrals, okay? And integrals are the area problems that we've been doing, okay? So before this, these were unrelated, but now we're going to see the connection, okay? The connection was discovered by these two dudes. You may have heard of them, Isaac Newton and Gottfried Leibniz. These two, by the way, actually discovered calculus basically at the same time, and they hated each other because one thought they were smarter than the other. I don't know which one's which. All right, so here's the fundamental theorem of calculus right here. We just wrote it in our foldable, okay? Remember, it doesn't matter the notation. We put f prime, they put little f, and then put big F of b minus big F of a, okay? But really what it's saying is that if you find the antiderivative, okay? So the antiderivative of little f is going to be big F, and you do f of your upper limit minus f of your lower limit, you're going to evaluate this, okay? And this is how we now are going to move forward into evaluating integrals without a calculator or without drawing a geometric shape. Okay, we're going to start getting these exact values. We were getting exact values on assignment number 6 because everything was a geometric formula. Okay, but again, now things are going to start curving Okay. And we're going to see how we get that. All right. What does this say right here? All right, so this is just showing the notion, okay, the notation, and these are the examples, but this gets a little hard to understand, so I'm just going to show you. So we're going to jump right into number 17. Okay, so now we're going to go back to back in January when we learned how to do antiderivatives. We've memorized some antiderivatives, okay, and then others we have rules to do, okay. So the first thing is the antiderivative. Okay, we're not going to worry about our upper and lower limits yet. The antiderivative of x squared, remember, is add 1 to this exponent, get 3, divide by new exponent. Okay, next piece of the function is we don't have an x, so we're going to put in an x. We do not have to put the plus c, so that's what this is explaining right here. It's not necessary to include the plus c. Okay. And we're going to do this from, okay, that just means from 1 to 2. We should have an equal sign right there. And what this means now is we're doing f of b minus f of a. We're going to plug 2 in to this function, minus we're going to plug 1 into this function. That is the fundamental theorem of calculus, okay? So the algebra gets a little like, a lot, but not difficult. Okay, we're going to plug a 2 in first. So 2 cubed over 3 minus 3 times 2. That's f of b. I'm going to write it this time, but we're not going to write that all the time. Okay, minus, now we're going to plug a 1 in. 1 cubed over 3 minus 3 times 1. F of b minus f of a is how we evaluate an integral. Okay, and real quick, I'm just going to tell you, I've been all those times that I was telling you the exact answers when we were doing LRAM and RRAM and all that stuff, and I was getting exact answers. I was doing them in my calculator, and I was doing the fundamental theorem of calculus, which is just simply you're going to hit math, and you're going to hit option 9. So we've done option 8, derivatives. Now we're going to do option 9, which is antiderivatives or integrals. Okay, and if you have 84 yours will look like this. If not, you do it the same way we did the is anybody out there have an 83? I can't remember if someone does or not. If you do, could you just speak up real quick?
Yeah, I do.
Okay. All right, Ella, if you do not remember that I showed you how to do the derivatives, it's basically going to be the same thing. If you want to take a picture of that, or if you wrote that down, you're going to still do math 9, but then you have to type in the function, comma x, comma the lower limit, comma the upper limit. Okay. So there's one more thing added from when we did derivatives.
Okay, thank you.
You're welcome. All right. So once we type this into our calculator, we literally would just go 1 to 2. We'd type in our function, which was x squared minus 3. And then we'd put our x in for dx. And it's going to tell us the answer is that. If we wanted a pretty fraction, we'd turn that into negative 2/3, okay? We're going to get negative 2/3 by hand, and you're going to have to do this by hand. Don't do these by calculator this evening, okay? 2 cubed is 8, so this is 8/3. 3 times 2 is 6. Okay, and then we're going to distribute this negative in, so it's going to be negative 1/3. And this is going to be negative 3, but distribute a negative in and get plus 3. So we have 8/3 minus 1/3 is 7/3. We have negative 6 plus 3, which is negative 3. And negative 3 is just 9/3 or negative 9/3. And 7/3 minus 9/3, negative 2/3, just like the calculator told us. All right, so the rest of this is we're just going to do examples on the fundamental theorem of calculus part 1.
Before you go,
Yeah.
can you explain where you got the x cubed from, or like how you did that part?
Yeah, okay. Remember like back in right when we came back in January, Okay, so do you remember how to take a derivative, right? So the derivative of x squared is 2 times 1, subtract
Yep.
1, right? Okay, so when you're doing antiderivatives, you're
Oh,
going reverse. You're going to add 1 to the exponent, divide by the new exponent,
all right, got
right?
it.
So 3x to the 0 is really 3, right? So you're going to add 1 to the exponent and then divide by 1, which still gives you 3x, right? So that's how you get that antiderivative.
Yep. All right, thank you.
All right, next one. Okay, going to throw a loophole right at you right out of the gate. Okay, it's the integral from 0 to pi over 4 of secant squared. Okay, so if you don't remember the antiderivative of secant squared, okay, it needs to be memorized, but it's in your foldable right here. Okay, who gives us secant squared? Tangent. Okay, so the antiderivative of secant squared is tangent. So this one's real simple. Okay, it's just going to be take the antiderivative, tangent of theta, and we're going to evaluate that from 0 to pi fourths. Okay, and there are other ways to write this. This is just the way I choose to do it. Some people write it like this. So this, I'm not going on to the next step. I'm just writing this a different way. They write it like this. Okay, you may see it that way, but it just simply means f of b minus f of a. Okay, so we're going to plug pi over 4 in, so we get the tangent of pi over 4 minus the tangent of 0. Okay, the tangent of pi over 4 is 1, tangent of 0 is 0, so this equals 1. So the antiderivative from 0 to pi over 4 of secant squared theta d theta is 1. Okay, remember, when we're doing definite integrals, we're getting a number. When we did indefinite integrals is when we would have written tangent theta plus c, and it's a family of functions. All right, any questions so far? All right, let's just go on to the next one. Okay, so number 19 is the function 3 radical t. Okay, well, we don't have the antiderivative of radical t memorized, so we're going to change that into 3 times t to the 1/2. Okay, we know how to do that, dt. All right, so now we take the antiderivative, add 1 to 1/2, and we get 3/2. Okay, we're going to have to start doing some stuff in our head, right? I'm going to divide this 3 by 3/2, which means multiply by the reciprocal of 2, which is 2/3. Okay, so 3 times 2/3 is going to give me 2. Okay, so the antiderivative of 3t to the 1/2 is 2t to the 3/2. And we're going to evaluate that from 1 to 4. All right, so now we're going to plug in our 4. 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Okay, you should recall that when I'm raising to an exponent, this is the root and this is the exponent, right? So I'm taking the square root of 4, which is 2. I'm then going to cube it. 2 cubed is 8 times this 2 that's out front is 16. So 2 times 4 to the 3/2 is 16. And then 1 to the 3/2 is 1 times 2 is 2. 16 minus 2 is 14. Okay, all the rest of these examples are just taking antiderivatives. Okay, so we just got to remember that property of how to do that, and then just evaluating with the fundamental theorem of calculus part 1. All right, so again, we do not know antiderivatives of quotients. Okay, we will learn that eventually, but right now we do not know it. So this is the antiderivative -2 to -1. And then we're going to divide this out. Okay, so u cubed divided by u squared is u minus 1 over u squared is u to the negative 2 du. Okay, so really all I did was I split up u cubed over u squared minus 1 over u squared. And then I simplified that to become this. I know how to take the antiderivatives when I have power rules. Okay, the antiderivative of u is 1/2 u squared, right? We're going to add 1 to that exponent, divide by that exponent. And then we're going to add 1 to this exponent, which gives me u to the negative 1. And I'm going to divide by negative 1, which is going to turn this into a positive. And we're going to do that from -2 to -1. Questions on my antiderivative?
Teachers and students, please pardon this interruption. At this time, we are going to conduct our monthly lockdown and evacuation drill. Once again,
All right, guys, I'm going to have to be quiet for this time. So you guys have a great day. We'll pick up tomorrow because we're having a drill. So there's no homework tonight. We'll just pick up here tomorrow. Have a great day.
So you will see some strobes in your lights and a message in your computer. Once again, this is just a drill. We